recording the video so we can like compile them. You can just try to watch it whenever. Okay, last week we did a bunch of drawing. My main takeaway for y'all is remembering the ideas of how many sticks who needs. So can we have a quick recap? Y'all can just say hydrogen needs how many sticks? 1. Okay, just fastest answer. Y'all can those online you can type or unmute and talk. Oxygen, how many sticks? 2. Okay, Keith said 2. That's correct. What about nitrogen? 3. Those online following, right? Okay. What about iodine? How many sticks would an iodine need? Where do you refer to? I mean, what should we look at? Okay, Jingwen said 1 is correct, but what should we look at? Yeah, Keith, you're looking at the wrong place. Right? If you're looking at all examples, then what if I give you a random? I give you astatine, you never see before. Then all examples that don't have. Keith, you know what to look for? And you don't know really. Exactly, you need to locate, then you can determine where's iodine. Then, knowing where iodine is, are you able to tell? Group 7, how many sticks? Yeah, okay, guys, when I'm asking you all these sticks questions, this is the place to look for. Okay, one more. Okay, I need those online answer. The people in class are doing okay. Xianghui not coming up. Okay, anyway, let's try. People online answer me. If I got arsenic, how many sticks would an arsenic need? You'll never get to draw an arsenic. I never draw arsenic before, but if you had to figure out how many sticks. Those online, please tell me how many sticks would an arsenic need. Y'all can type. Are y'all typing already? How do I check? Sorry. Oh, no, nobody's typing. Okay. Arsenic is here. Okay. Kelly said 3. Do we agree? Yeah. Okay, so even the weird guys, y'all can tell. Okay, last one. Sulfur. Type or say anybody can do. 2. Okay, so if you master this, Clarice, good job. 2. If you master this, I'm sure you are very, very comfortable drawing random stuff. Anything really, I can give you a random molecule you can draw. So last week I said this 2 is way beyond what you're supposed to do. Right? The first one, I'm just gonna draw for fun. You can copy in your notes. Totally cannot be tested. Even JC people cannot do this. I'm sure. But if you follow the concept, you're fine. So I teach you how we figure this thing out. You can copy for fun. No need to learn. But I think it's interesting to know that the knowledge you have now should apply throughout, no matter this molecule. I don't even know whether it's a real molecule. It doesn't matter. So I tell you how to break down. I look at the first part. I see a CBr3. I quickly run through my head. C needs how many? Can even write down. C needs how many? 4. Br needs how many? All right, let's do all first. Let's write out for all first. Br needs. Quick check. Very table. Quick check. Bromine, 1. Carbon again, 4 again. Oxygen, 2. Okay, carbon again. Hydrogens, 1 each. Nitrogen, hydrogen. Okay, all correct. So this is not enough. Like knowing this is still very difficult. So I tell you how we break it down. Somewhere it's a bit late. Okay. So I figure out the CBr3 first. You see, Br only 1 stick. Br, Cl, H only 1 stick. They cannot be inside the molecule. They must be on the perimeter of the molecule because you cannot extend already. So the only way to start the molecule here is like that. This is the one and only way. Does it make sense? Because BR cannot extend, so I cannot put BR like here. How to go? Cannot go already, ma. So I must put it at the surrounding lah, wrapping around like that. So this is how we start off. I'm following left to right. So CBR3, this is the only way to draw it. Then I connect into a C, must be a single bond one, because this C maxed out already, ma. This C only can have 4, 6. I already drawn 3 for him already. I only can single bond. Now I got this OOC. It's a bit difficult, but because I've done this before, I can come out with a good idea. I give 2 bonds to the O, so I settled the first O because O needs 2 sticks, ma. Then the other O needs 1 stick. I cannot do like that. You know why? Then C explode already. Not just the C explode, then the next O, this one also cannot carry on already. Because 2 sticks done already, ma. So must be 1 stick. No choice. Then this is the only way the molecule can keep drawing. Then I'm done with this O already. Then since O only can take 2 sticks, I only know this is the only way. Naturally, I flow into a single C. Just now we said H also need 1 stick, H 1 stick, so you cannot continue H, because H cannot already. This is wrong. So my 2 H's, I'm choosing to draw them where? Up and down. This is the only way. Right? Now, this C, 3 stick already. Right? How? Only can 1 more. And wow, very happy, done already. Why? Because nitrogen needs.
Sorry, I have some issue.
Hey, no worries, I'm recording also, we can go and watch. But anyway, I'm doing this for fun. This won't be tested. It's too difficult. Okay, but after N, who can complete the diagram for me? 1 per side. This is the answer. Right? Honestly, it's not difficult, right? It's quite fun, in fact. Really, I think it's fun when we do this. Okay, so I'm just showing you all for fun. No need to learn. No need to remember. Xianghui, I'm just teaching them how to draw a crazy molecule. This one, if you all go Sec 4, no, Sec 4 also don't do it. It's too difficult. Okay, we try again. I erase a bit. Hey, sorry, did you all copy down? Online, copy down. Xianghui is okay if you miss, you just go and watch. But we'll do the same exercise for the last one. Anyway, we are on page 7 of your notes. Last week we stopped here. Okay, I mean we didn't stop here, I just skip this. Okay, now quickly think of the sticks. Carbon is 4, chlorine, bromine, all 1. Because they are group 7. Carbon is another 4, oxygen is 2. Nitrogen? 3. Hydrogen? 1. Carbon? 4. Then hydrogen and chlorine all 1 again. Right, so mentally know what's going on. Then we start left to right. Same thing. I see a carbon to start. I'm following carbon with Cl2Br. And they all only can take 1 stick. Same thing. There's no other way to draw it. I must surround it. I must surround carbon to the corners with 2 chlorines and 1 bromine. No other way. Because just now when Xianghui wasn't here, I was saying you cannot put chlorine here because after that it cannot extend already. Chlorine only can take 1 stick. So this is the only way to start. Then, what is the next atom to follow up with? After this Cl2Br done already, what's the next atom? Carbon. Naturally must be how many sticks? No, continuation from there. Must be 1, no choice, right? I'm done with this already. Now, this ONH is a mouthful, it's a bunch of things. So this one, if you never learn Sec 4, you all learn a bit of this. There's a particular pattern, but since you never learn, I'll just give you the answer. I put a double bond O, single bond N. Okay, doing that satisfies my carbon. All right, then I move on to N. N is how many sticks? 3. Now, how many have I given him? 1. I need to 2 more. Aga. Then, just nice, very lucky. H come immediately. H needs 1 more, just nice. Put it here. Then I can continue drawing already. So I'm done until here. All right, now I need, naturally, it's a C and it's a single stick. I decided already. How do I finish up the drawing? So I'm done with this C already. The rest very easy. I need 2 hydrogen, 1 chlorine. There's only 1 way to put it. Surrounding or single. This is the answer, right? Really fun to do, really enjoyable. Okay, so just copy this down, but as I said, won't be tested. But this idea will follow you until Sec 4. The idea of how many sticks. Okay, this one cannot change one. Okay. Last week, did we clear this? Haven't. Okay, we continue. Okay. Now, let me preface this first. Combined science, only this. So there's no 1 and 2. For combined science, there are 1. Yeah, just 1. So combined science, you all will learn until this page, which is what you have. Later on, I will teach the pure science also, the next page. So what you generally know is covalent structure actually got 2 types. And both types are entirely different. So they have different properties. One is hard, one is soft, one is easy to melt, one is hard to melt. They are completely different. You all are learning the 2 physically here just nice. They are learning the simple. Okay. The pure later we will learn the giant, which is not simple. Okay. So, but good for you all to listen in also. So it's quite interesting to connect the dots, because in school you all won't learn this. Now, covalent structure, simple, there's another word for it, discrete. They exist in discrete molecules. Discrete means individual / separate. Discrete. Yeah, discrete molecule. So in JC, we start to use the word discrete. I don't know whether that's spelled correct. Discrete. Yeah, correct. Discrete. Okay. It's double E. Okay. The meaning of discrete molecules, so simple. They exist as discrete molecules means 1 by 1 molecule. See, look at this drawing. This is 1 water molecule. This is second water molecule. How many water molecules can you count? 5. So what do I mean by simple, discrete, individual, or separate? These 5 molecules, are they covalently bonded with each other? Yes or no? Are they? You can vote. Do you think there is a covalent bond in between particle A, molecule B, molecule C, molecule D, molecule E? Do you think they are covalently bonded together? You can say yes or no. I don't know. Xianghui says yes. Anybody? You can be wrong. It's okay. I haven't teach you this. So covalent bond be okay. Most of them say yes, so I assume you all might be thinking yes. Okay, answer is no. Okay, you see. We go to any of the earlier molecule you do. This is a nitrogen molecule. Internally, a nitrogen atom is stuck to another nitrogen atom. Agree? They are glued together. Correct? This is a molecule. Internally, there is a strong covalent bond holding them together. What if I draw a next door nitrogen molecule? I just anyhow draw, but this is molecule A, this is molecule B. Molecule A and molecule B, do they have the same kind of covalent sharing? Because covalent, what's the definition of covalent? Covalent share. So when you share electrons, you get stuck together, you're locked together, you glue together, cannot move. So I'm asking, is molecule A covalently bonded to molecule B? Right, the answer is no, right? These two, in between them has no covalent bond. No covalent bond. No need to copy because I'm just using the nitrogen example. We go back to the same page in your notes. Can you see that molecule A, B, C, D, and E? They have no covalent bond in between them. What they have is covalent bond inside of them. You understand the difference? So internally, they are covalently bonded. Externally, they are not. So we read the notes. So simple molecular structure are found in elements and compound. How come got element compound? We can write example. Elements can be, who can give me an example? A covalent element. It's not easy. It's a bit confusing already. Okay, so far, Xianghui O2. I love it. It's very good. Give me more. A lot of 2, 1, something 2, something 2, something 2. F2, H2, all correct. And just now the earlier when I scroll up, I use N2 also. They are elements. We went through this earlier. Element means what? Element means they belong to one finger, right? One finger can find them. So nitrogen is N2, it's made of 2 atoms, but you can use one finger to poke it, that's nitrogen, right? So that's That's an elements. Compound. Give me a few examples of compound. CO2. My favorite example is also CO2. I have another favorite example. It's on your screen. H2O. Very good. Compound means you have two or more elements stuck together. And these are all can be forming small molecules. Now, the next sentence is important. Within the molecule. Just like I said, internal to the molecule, is there covalent bond? Yes. Strong covalent bond. Keyword is strong. Internal to the molecule. Just now I said nitrogen, the N1, nitrogen 1 and nitrogen 2 that stuck together very tightly. External. That means between molecules. Between means externally. You can write down the word externally. Externally. Externally, they don't get to enjoy such a strong bond. The correct phrase you must memorize is weak intermolecular forces of attraction. Some schools, they let you write the short form. Van der Waals is the person who found this. So we call it the Van der Waals force. So weak intermolecular forces of attraction. 5 words, you cannot miss a single word. Some schools, you check your teacher, can you write Van der Waals forces? Some say yes, some say no. So if they say no, then you go weak intermolecular force of attraction. So how do I explain inter? A lot of kids don't know why the word inter comes out here. Intermolecular. You all know what is interclass? You all play interclass? And now maybe cannot play. Can play, cannot play. But you all would have known what is interclass basketball, interclass football. So what's interclass? Different classes compete together. What is inter-school? My school, play your school. What is international? My country versus your country. International football competition, international basketball, right? What is intermolecule? I mean, yeah, intermolecule. Different. So the relation between different molecules. So can you see that intermolecular? This word comes from the word inter and molecule. So can you see all these red dots are? You don't need to know how to draw, but you must see that all these red dots are what we are calling intermolecular forces. Are they strong or weak? Weak. I'm going to change yellow. Yeah. What do you call this one? Strong or weak? Strong. Covalent bonds are strong or weak? How strong? Mighty strong. Okay? I'm saying this because so many people think that covalent bonds are weak. But they have made a mistake. Covalent bonds are not weak. What is weak? The only weak thing is, I must say properly, the intermolecular forces of attraction. So please take a red pen, whatever. Strong, weak. Know what is strong and weak. Half my students who don't learn Sec 3 properly, they go to Sec 4, they keep thinking covalent bonds are weak. Common mistake. So please know what is strong, what is weak. Okay? Now, please note that this is a tidbit. It's interesting to know. Van der Waals forces, I just write short from BWD, BDW, sorry. Van der Waals forces is related to mass. Basically, what am I trying to say? Higher mass, higher Van der Waals. Okay, this is just something that you will eventually observe next time when you do harder questions. So if I ask you, CO2 versus H2O, whose intermolecular force will be stronger? Knowing that I just give you this fact, this knowledge that higher mass, higher Van der Waals. Okay, Clary said CO2. Why? Clary, you're right. You're right. But why?
Higher mass.
Higher mass. What is the mass of CO2? Next time when you're pro, it's in your brain already. No need to count. It's good for your chapter, next chapter. Must calculate all of it. 44. Versus? Hey, you know how to get 44? Yeah, okay. What about H2O? Somebody else tell me how heavy is 1 unit of H2O. It's good, All these things, when you memorize, you save a lot of time. But now you can count lah. You add. No, where do you go? Go periodic table. Everything in exam you have no notes, man. You only have periodic table. So 2 H's and 1 O lah. 1 plus 1 plus 16, 18. So who is the winner? CO2 is higher van der Waals forces, which means what? These little dots are more intense, stronger in CO2. So if I want to vaporize CO2 and I want to vaporize H2O, which one easier to vaporize? Weaker lah, easier to destroy H2O. Which one harder to destroy? Okay. So to overcome these van der Waals forces, which one need more energy? CO2. Whose boiling point higher? Yes. So write down. Therefore, CO2 has higher BP than H2O. This is just a tidbit knowledge. Y'all won't be needing this so soon, but I think it's interesting to know this. Next time you can draw that, you can connect different chapters to this. Okay, they will ask you on fluorine or chlorine has higher melting point, a boiling point. Now you know that. You can count yourself. Okay. Now, the next 3 lines in my table look very harmless, but this is where all your marks is. Understanding what I just told you gives you concepts. Concepts don't become points. You want to go exam score points, you memorize this table. Okay, I'll explain this table, but you must memorize. So they will ask you, why would simple molecules always tend to be liquid or gas in room temperature? They will ask you this question. You have to say every single word here. They ask you, how come water is liquid in room temperature? We all know water. Isn't this water? We all know water is liquid in room temperature. They ask you why. You just copy this off. Weak intermolecular forces of attraction between water molecules require little amount of energy to overcome. Therefore, water has a low boiling point. Can you see how I kind of take this explanation and phrase it to answer for water? Right? Basically, I'm using all the same keywords. They can ask the same thing. Why is hydrogen a gas? Okay. Jingwen, read me the answer. You can copy this. They ask you, why is hydrogen a gas at room temperature? I mean, if you copy it word for word, can lah. So, I mean, Jingwen just read out the whole note. Good enough lah. But if I were answering, I will try to show off. I'll tell the examiner I'm very smart. I say, weak intermolecular forces of attraction between the hydrogen molecules require little amount of energy to overcome. Therefore, hydrogen has a very low boiling point. Right? I mean, I'm just adding little things to make the answer fuller and nicer, but basically the keywords are all here. Okay? And they must say room temperature. So you see, water, is it always liquid? It's liquid in room temperature. But what if I bring you to the volcano? Water is steam. So you must give a temperature. So usually we say room. Room is 25 degrees. If you didn't know, write this down. Room is 25 degrees Celsius. Okay? And of course, the second point is kind of repeat. Why would, they can ask, why does carbon dioxide have a low boiling point? I mean, if you have low BP, you have low MP, it's the same thing. They are all parallel one. Low MP, low BP is the same thing. You have low boiling point means you have low melting point. You can no such thing that you have low boiling point but high melting point, no such thing. Everything, if you have high BP, high MP. So when we describe simple covalent, we say that they have low MP. Why? Say the same thing. Weak intermolecular forces, blah, 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 blah. And I bolded the word overcome. Because as you all learn, you will know that sometimes you might access this, use the wrong word, not break. Because many of you will start using, it will require very little energy to break. Because it sounds like you're breaking that part. Don't use the word break. If you use the word break, you lose 1 mark. In forces must be overcome. This is just English. Forces must be overcome. Okay? Pay attention to the little bracketed. This one not answer, but you need to understand. When I vaporize my water. This is 5 water molecules. When I separate them, when I successfully boil it into steam, what happens to each H2O? Still H2O. Are you able to cut away the H? Cannot. Y'all cannot do that. So when I melt or boil water, what am I destroying? The same words. What am I not breaking or destroying? Yeah. See, the covalent cannot break one. If you can break, you should be at 1000 degrees Celsius. Can't even break at 1 degree. So it's crazy strong. Okay. Now, why do they conduct electricity? You ask yourself, carbon dioxide, hydrogen gas, nitrogen gas, water. Actually, by right, pure water, they don't conduct. Okay, you all quickly write. This is important. This is difficult now. To conduct electricity, you must have. You need mobile ions or mobile electrons. You need mobile ions or mobile electrons. Okay? So anything that has mobile ions, this one must copy down. It will keep coming up. If you have mobile means what? Can move. Okay? If you didn't know mobile means can move, just right now. Mobile means can move. Of course, you don't write can move in exam, you write mobile. So you ask yourself, Lord, H2O got ions. No ions. So don't even talk about ions. H2O, no ions, can't even move anything. No ions, how to move. H2O got electrons. Everybody type yes or no. Does H2O have electrons? Because I'm trying to think about this mobile electron. Don't talk about mobile first, talk about electrons. The 2 in class said yes. What about the 3 online? Do you think water has electrons? You can say yes, no, or don't know. Shall we say should be? Okay. Okay, of course it has electrons. Why? Everything has electrons. Hydrogen got electron. Oxygen got electron. Have right? Gold got electron. Arsenic got electron. My face got electron. The sky got electron. The air got electrons. Everything got electrons. Every atom is made of 3 subatomic particles. This is two lessons ago. What are the 3 subatomic particles present in every single atom? Proton, neutron, electron. So H2O is just a combination of 3 atoms. If one atom already got electron, how can 3 atoms do it? So everything has proton, neutron, electron. But my question is now, are they mobile? Are the electrons freely flowing inside a cup of water? If it is pure H2O, we look at a drawing of H2O. I just draw it. H2O. Just a speed drawing. Okay. Is there any electrons that are free? That means zipping around. That means free to move outside the molecule. No. All the electrons that H2O has, they are not moving. Okay. So can H2O, pure H2O, conduct electricity? Pure H2O. Not the swimming pool H2O. See, in the sea, you get lightning, you die. But pure H2O cannot conduct. Pure carbon dioxide cannot conduct. So all simple covalent compounds cannot conduct. Why? Because they do not have free moving ions or free moving electrons. Okay? Anything that has free moving ions will conduct. Anything that has free moving electrons also will conduct. Anything that has none, of course, will not conduct. So every time you ask yourself, is something a conductor? Does it have free what? 2 things. You have to check yourself. Free moving ions or free moving. If I pass one of them, I check one of them, then can already. You won't have things that can check both one. So it's either lah. So you should add the word either. Either free moving ions or free moving electrons. Okay. Then unfortunately, simple covalent structures have none of those. So they cannot conduct at all. Okay. Common examples, I actually wrote memorized, but then I put a star at ammonia. I just feel that ammonia is the big one to memorize. The rest, you look at the table, the rest you can use common sense. Right? Can you all just scan through this table and tell me, I believe so lah. Most of them are common sense. You just need to know a few prefixes. Mono means, I don't know. Mono means one. Di means two. Tri means three lah. So if I tell you what is a nitrogen dioxide, you kind of can guess, right? Would it make sense that nitrogen dioxide is NO2? Would it make sense? I know I haven't talked about it, but if I ever say carbon monoxide, you can guess the formula is it's just a CO, right? If I never teach you this, but if I ever say hydrogen iodide, you kind of can guess it's HI, right? Hydrogen sulfide, how come it's H2S? Because you need to crisscross. Remember the crisscross lesson we had? How do I know S is 2 minus? Two what? Key say group 2 is wrong. I mean, I'm happy you're trying to memorize without looking, but don't mess up this. It's group 6. So everything group 6 needs, you're 2 steps away from stability. So you need to get 2 electrons. So you crisscross this, you get H2S. Also can work it out. Like bromine, what kind of Br2? Because Br alone is unstable. Does this thing exist in the world? Cannot exist. Too unstable already. So what we do? Find another guy equally unstable. Isn't this the dot and cross lesson we just had last week also? See, everything will connect to each other. So bromine is naturally Br2, no other way. Right? You can want to put Br3 also cannot, no space really. The bromine only one stigma. Right? So most of this table, no need to memorize. Why I put a star here? Because this one, ammonia, how do you remember ammonia is actually you can't. You have to remember. But it's not difficult, because why? Now that we are experts at sticks diagram, ammonia need how many sticks? N needs how many sticks? 2, check. 3. Okay, N needs 3 sticks. H needs. So how do you draw N and H? The only way is NH3, right? Because you need to give ammonia N 3 stick and then you're gonna stick it with H's. So ammonia is NH3. Not very hard to memorize. So this whole thing you must know lah. Don't need to memorize, must know. Okay. Now, combined students chill, listen for fun. Pure students listen closely. This is very, very important and confusing. Okay. Simple are discrete. Discrete means one molecule and 2 molecules, they have no real relationship. What is their kind of partial, weak, marginal relationship? What do they have? Y'all can answer. Molecule A and molecule B. If I have molecule, water molecule A, water molecule B, what is the existing interaction between them, which is insignificant? Weak intermolecular force attraction. So they are discrete and separate. When we talk giant, they are a giant network. That means they are endless. That means this is eventually that I'll draw some drawing, but what happens is everything is one molecule. Everything is connected endlessly into one molecule. So it's quite crazy to think about it. Like diamond. Diamond is one molecule. But we don't even call it molecule because one diamond is made of how many carbon atoms? 1 trillion. I don't know how many, but too many. Right? So what happens when things covalently bond, one atom covalently bond to the next, 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 and it's endless. And that's not that we don't even call it molecule then. It's not molecule, it's a network of endless atoms spreading and spreading. Okay? Each of them are covalently bonded throughout the whole structure. So you want to think of it technically is one molecule. Okay? If we look at some drawings first, these are the 3 examples that are tested for O-level. Diamond, we talk about it first. Diamond is carbon. So how do you draw diamond? I just draw here. No need to learn. Diamond, carbon is how many sticks? You can answer. C need how many sticks? 4 sticks by right. So 4 sticks. So what happens is this 1, 2, 3, 4. So what happens if I put carbons here? Is it stable? I should ask you. I mean, y'all can think about it. Is this stable or not?
We just see yes, but the outside.
Everybody else is stable. So how do I stabilize this? Give him how many more sticks? This guy. 3 more. Tap, tap, tap. This guy. 3 more. Tap, tap, tap. This guy. This one no space, don't draw, but you get the idea. Then what if I put C's onto them? Same thing. C, 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 C. What if I put C's again? Yeah. This is diamond, no? The whole piece is one piece of diamond. Right? So one diamond is how many molecules? It's technically one, but yes, don't call it molecule. Don't call it molecule. It's just one giant covalent structure of endless C's. When does it end? It ends when there's no more C. If I put 1 billion C, they all network into one piece. Okay. If I put 50 C, then it's small diamond. Okay. So diamond is an example. It's the easiest example. We talk about the properties first, then we talk about the 3 examples. Okay. Because it is endless, do they have van der Waals forces? Yes or no? Is there any discussion of van der Waals forces? Online people must answer. Hey, y'all should unmute. I'm not talking to the combine anymore. Pure, please unmute. We get this going faster.
No.
Okay, no van der Waals. So everything is rock hard, solid, super mighty, strong. Strong what? What bonds? What are the interaction between each carbon atom that I drew just now? What is the relationship? Covalent. Covalent strong or weak?
Strong.
Super mighty strong. Okay, so that's why they are solid. They are solid in room temperature and very high. How to explain? Please memorize. Okay, pure student, I trust that you all can just read yourself now. Extensive network of strong covalent bonds throughout the large amount of energy to distort. So you don't destroy it so easily. If you can crack diamond, diamond is the hardest substance in the world. You crack it, you are very strong. You need. I don't even know how they cut diamond. Because diamond, you use diamond to cut rocks. You know, when they're excavating, they're digging deep holes. The tunnel digger, they use diamond. They use diamond to dig it. Because if not, the rocks that are so hard, the bedrock will crack the drilling tool. So you cannot use metal. You must use diamond. Okay, quite fair. Then there's an exception of graphite. Those pure, it is right, the graphite is soft. It's a bit weird. So graphite is full of weird. Later we'll talk about why. Okay, so typical giant network atoms are mighty strong, except graphite. Then the second point, quite easy to explain. High MPBP, because covalent bonds are strong or weak? Super mighty strong. Strong covalent bonds. How come we use the word break? Just now I said don't use break. It's because when did I say, just now earlier we said use the word overcome. What do we overcome? One word. You can overcome a. You can look at your notes.
Force.
Overcome a force. When there's a bond, you do what to it? You break. I mean, you all don't need to know, but yes. So choose the correct word, because here in my screen, it's not in the notes. Okay. If you use covalent, if you use overcome, you say every single word. Large amounts of heat energy required to overcome the extensive network of strong covalent bonds, 0 marks. Okay. It is this cruel. You use the wrong word, one wrong word, 0 marks. Please. Okay, so this one is pure science. Please write. Not overcome. Vice versa. So when we talk small discrete molecules, we say overcome. Here we use break. Now, it's insoluble in water. Same thing, covalent bonds are very tough. You cannot do much to it. Last point, does not conduct electricity. You ask yourself the same question. Will diamond have any spare mobile electrons and ions? Answer is no. But again, graphite can conduct. So we learn graphite because it's full of exception. And later we'll talk about why. Okay? Pure students following, raise your hand. No need to memorize all. Of course, day one, you take weeks to memorize this, but just understand. Okay? And of course, I'll upload this so you can rewatch. Now, diamond and graphite. Graphite is the guy that's full of exception, the weird one, but they are both made of carbon. They are allotropes of carbon. So those of you who didn't know, Of course, you all wouldn't know. The word allotrope. Allotrope means same element, but they are in different forms. So just now I drew a bad-looking diamond. Later I'll draw a bad-looking graphite. Okay, but don't need to draw for exam. So diamond and graphite are both made of carbon. They are both the same element. That's why a lot of people are very funny. They say the girls like wedding ring. They like diamond rings. One diamond ring, 5K, 8K easy. But if you have a pencil, what's inside the lead is also diamond ring. It's the diamond. It's 100% the same element. It's just arranged differently, and the price is different. This is not even 1 cent, right? For the same amount of carbon, you go charcoal, you barbecue that charcoal, that one also carbon. But then that one you cannot use it to propose to your wife, right? So that's the joke. My teacher always say, if your wife want diamond, you can give them pencil. Okay, so graphite is inside your pencil. They are all made of literally purely only carbon. Now, the structure, unfortunately, pure science, you all better memorize this. Okay, it's difficult. We go through diamond first. Diamond we talked about already. Each carbon is bonded to 4 other carbons, right? And it just goes on forever. So because each carbon is fully occupied, there's the word tetrahedral, also memorized. Tetrahedral means 4-sided. Okay, please copy down. Tetrahedral means 4-sided. So because I said each carbon connect to 4 carbon, each following carbon connect to 3 other, because one is really taken. So everybody will be 4-sided. So the word is tetrahedral. We talked about this already. High and high MP, and it's the non-conductor because no spare electrons dangling around. So diamond quite straightforward. Now, what's difficult is this one. Very challenging to memorize. For graphite, carbon supposed to have 4 friends, right? But you only bond with 3. Okay, so how does it look like? So first thing is already a bit weird. Graphite is full of exception because a carbon supposed to have 4 sticks, but this one only got 3 sticks, which means you got 1 electron there waiting, right? No friend, nobody come in. What about the second carbon? Supposed to have 4 sticks, but only 3 sticks. So got 1 electron standing there waiting, nothing happens. Next carbon, supposed to have 4 sticks, but 3 sticks. So 1 electron there standing. Next carbon. So these guys become, okay, those online are following what I'm drawing. I mean, this is a bad drawing. It's not even proper, but the idea is there. So you must know that graphite is different. Why? Because each carbon only connects into 3 other carbons. Therefore, it becomes surprisingly an electrical conductor. Can you all see the loose electron? This is mobile electrons.
But why 3?
No, it's just the naturally they form this way. So naturally, there are excess electrons flowing all around that, all through that graphite. Have you ever seen YouTube video? They take a pencil lead, then they can conduct, and then the light bulb can light up. Have you ever seen it before? You can Google They can a normal electric circuit. They put a piece of pencil lead in between, and then the light bulb can light up. Why? Because you have all these free electrons helping me carry the charges. So this is the first exceptional point about graphite. It is an electrical conductor, okay, and it produces delocalized electron. Anyway, you all should listen, because same when you are doing well, what if they ask you whether you want to take pure? I suggest you take it. Will they ask you, or did they ask you already? No. You got chance? You say no. Ayo. Drop what? Oh, you like human? Are you strong? Human. Because humans is tiring to study. Like for me, I'm lazy. So I feel when I was a student, I love AMAT, EMAT, Chem physics. No need to study, just understand. Like if you have a good brain, which I think you have, you understand, then no need to study. Imagine O-levels, you have studied 3 humans, which I also had. I had Geog, SS, and Lit. I memorized like crazy, like dog every single day. Memorize all the answers, So you all can start thinking ahead. So if you all get the chance to take pure, really much less to study, and it's fun. Don't you think this is more fun than reading the literature novel or SS, reading the wars and Norwegian, Northern Ireland, all that weird stuff, So I recommend. Anyway, first exception about graphite is that it can conduct. So it's a bit weird. Now, even weirder, they are soft. Just now I keep saying that giant covalent should be mighty strong. Every covalent bond is strong. But how come it's weak? Because graphite is not like diamond that is connected endlessly. Graphite actually naturally forms itself into sheets. 一片一片. So this is sheet 1, this is sheet 2, this is sheet 3. Of course, it has more than this. We just show 3 sheets. Okay? And don't need to ask why, just know that they are arranged in sheets. So the first sheet now is acting as if like it's one molecule. Second sheet is its own molecule. Third sheet is its own molecule. Now, between molecules, what do we learn? The combined science can answer. In between them, they should have weak, weak intermolecular or van der Waals force. Here also. Okay. Jingwen was trying to say the weak intermolecular force relation, but when I teach, I just say VDW. You all get the same thing, it's the same idea. So because they are arranged in sheets and they are not fully covalently bonded, so sheet 1, sheet 2, sheet 3, no covalent bond. In between them, inside them in between them we have weak intermolecular. So do you think there's a strong resistance to prevent sheet 3 from leaving sheet 2? Is it easy or difficult to separate sheet 3 and sheet 2? Easy, very easy. So that's why your pencil graphite, when you write on a piece of paper, how come you can leave a trail, you can leave a pencil mark? Because sheet 3 is leaving sheet 2. I mean, it's not so simple, but as you draw a line across, you can see a pencil mark because you are just shedding off the sheet. 一片一片, 一层一层 fall on your paper. That's how pencil works. Okay? So that's why graphite is soft. Okay? But still, they still have strong high MP because to melt graphite, you don't just melt. It's not enough to just melt this away. You still need to break all the covalent bonds. Easy or difficult? Not just difficult, nearly impossible. So if I want to take graphite, the pencil here, and I melt it, you think we can do it normally? Cannot. But if I want to break it or bend it or slide it, can very easy. Can you understand the difference between these two allotropes? Understand? Raise your hand. Yeah, difficult stuff. A lot of content. So we quickly compare graphite and diamond. This is a quick summary. So can graphite conduct? It can. Diamond cannot. Who is hard? Diamond or graphite? I mean, common sense. Diamond is very strong. Graphite is not strong. Who has high melting point? Both. High melting point, right? Both difficult to melt, right? Why am I only talking about diamond and pencil, right? Because luckily, the third one, usually we don't study the third one. Why? Silicon dioxide, just need to know the chemical formula is SiO2. It's written there already, don't need to copy. It's sand. What is sand? You go Sentosa, literally that sand. Literally Sentosa sand, okay? It's made of silicon dioxide. You might be wondering, hey teacher, but sand is so soft. Is sand soft or hard? But how come sand is so soft? I mean, you go to the beach, you walk on the sand, you know sand is soft. But how come I'm telling you sand is hard here, but you go to the East Coast Park, sand is soft? Because it's very small, so each grain is very hard. But I give you 1 million, or not million, 1 crazy zillion piece of little grain of sand, you feel soft because you're stepping in between, got air and all that. But if I take out 1 grain of sand, it's as hard as diamond. Not as hard as diamond, close to as hard as diamond. Okay? How come I don't teach a lot of SiO2? Because you realize this and this is almost the same. Every single line is almost the same. It's also tetrahedral. No need to know how to draw. I also don't know how to draw. Each silicon is attached to 4 oxygen atoms. Don't need to know why. Just memorize. But other than that, every description is the same. So before I go to exam, I usually just memorize the difference between graphite and diamond. And if they ever ask me SiO2, I just use my information from diamond to transfer. It's the same. So you see, it shares exactly the same property as diamond. So no need to memorize double. Okay. So if I ask, can sand conduct? Answer is no. Right? Y'all get it? Y'all get it? So the only difference is here, the first sentence. Each silicon atom is attached to 4 oxygen atoms. Then the rest you can memorize and copy exactly the same. Okay, actually that's it already. Can any questions for Pure?
Wait, so we only need to know these three, right?
Yeah, only this should be tested unless they give you a source-based question, which means they give you a small report or essay about a different giant, then they have to detail all the description inside. But in syllabus, it's just these three. In the rare cases, they give you a source-based question where you read and understand the question during exam, and that one, I don't know. Can? Okay, and very luckily, combine still can show because metallic also not tested for combine. Okay, but it's very short. Metallic is very easy. I'll take 10 minutes to go through. Now, although it's not tested for you, the concept is transferable. We zoom in. This is a lithium atom. Can you verify for me, is this the correct drawing of lithium? How do I check if this is the correct drawing of a full lithium atom? What do you check? Check the proton number. Can you check proton number for lithium? 3, right? So is drawn correctly. How many electrons then? Is the configuration okay? 2, 1. Can you see it's 2 and 1? 2 inside, 1 outside. Then can you see there are 3 neutrons? Nothing much. So this is just a typical lithium lithium atom. Keyword is atom. Why? Because on the next row, I show you we learned this last week. I show you a lithium cation. This is literally what we learned last week. He ejected a free electron. Right, so this one is consistent with what you already know. Now, this is one piece of lithium striving to get stability. He's hoping to get stable. What did he do? He kicked out his last electron. But usually got people take one. I mean, lithium chloride, the chloride can take. But now no chloride, how? Who is going to take this? Nobody is going to take it. Okay, what happens is, I drew 6 lah. I just copy and paste 6 of them. But in real life, it's not 6. It could be 6 billion. Imagine 6 billion lithium atoms all at the same time kick out 1 electron. So how many electrons do I have dangling around? 6 million. So this becomes how a metal is structured. It's very weird. Nobody take that electron, but somehow all the lithium, I just draw pluses, all the lithium cations surrounded by their own ejected electrons. This is actually what's happening in real life. So this is C of pure science you can copy. Delocalized space electrons. The blue one. C of delocalized electrons. So what is the forces holding a metal together? It is the pluses and the minuses. Where does the plus come from? You all can answer it. You're following. Who is the plus? In this drawing, who is the plus? Who has a positive charge? My lithium ion. Doesn't have to be lithium. Don't need to be lithium. Can be iron, can be magnesium, can be sodium. All the same thing. Who is the negative charge? All of the electrons that they delocalize, that they kick out. So the pluses and minuses, I draw some minuses here. So it's a lot of minus charges surrounding the pluses. Then plus and minus will attract, just like North and South Pole. So now they glue together. So you all can imagine the electrons are like glue. They are gluing the cations together. Now this is a piece of metal. Okay. Then of course the explanation is here, like you can read yourself. Each metal gives out its own valence electron to become a cation. These electrons end up filling the gaps in between the ions, and this is what you memorize. Pure, please memorize. What is a metallic bond? A metallic bond is the between positive metal ions and, just now I said this word already, C of negatively charged delocalized. Word for word memorize. We use the word C because it's quite a good description because it's like surrounding. So it's like you're swimming around, the cations are swimming around a sea of negatively charged delocalized electrons. Now, there's a word called electrostatic. You all can participate. When did we see this word in this chapter earlier on? We all, in both pure and combined, saw the word electrostatic in this chapter. I want everybody to go and research now. Go. This is important.
the structure, ionic. Is it the ionic structure?
Ionic. So how come they reuse this word? It's not for fun. They reuse this word because y'all don't need to use this word twice. Y'all only need to use this word in ionic. But of course, it's good to know why this word even exists. So who knows what is electrostatic? For pure, y'all must know why this word will show up in two different topics. I mean, two different subtopics. But for y'all, you need to know what does the word mean. Who knows? I probably said it during when we talk ions also. So how come this word shows up in ionic bond also? Anybody? No. If overall a force, then I will see this word in covalent also. Nobody knows. I'll just say that. The word electrostatic means between. Y'all can go to your ionic there and write down if y'all didn't. The word electrostatic. Okay? Write the meaning of it like between positive and negative. Every time you have an interaction, all must copy down, it's very important. Every time you have an interaction between positives and negatives, we call it electrostatic. So, do we have positives and negatives in ionic bonding? Ionic bonding, yes. Who is the positive charge? That's the name for it. Who has the positive charge in ionic bonding? It's easy. The what ions? Cations. Who has a negative charge in ionic bonding? Anion. So together, they are the attraction of pluses and minuses. So what can we describe the forces in between them? Electrostatic forces of attraction. Here, how come we use the word electrostatic? Because also got plus and minus. But who, in this case, who is the plus? Who is the plus side of this equation? In this case, lithium, but in other case, can be lithium cations. Who is the negatives of this scenario? Any anions? Here? No anions. So it's between the cations and the very long C of delocalized negatively charged electrons. Yeah, so that's why we have this word electrostatic. Okay. What kind of structure? If they ask you what is the structure, memorize this line. They are packed closely in a regular pattern to give a giant metallic lattice. Okay, nothing much. Just memorize the word giant and metallic lattice. Okay, giant, same thing is endless. How come is every time anything is endless, we call it giant? Just now we said giant covalent because the diamond, the CCC can grow forever. What about this lithium? I drew 6 of them. Could I have drawn 10 of them? It's the same thing, right? If I drew 100 of them, do I need to stop at 100? No need. I can do 1 million. So things that are endless, we call it giant. Don't say endless in exam, but you get the idea, endless. Okay? Metallic lattice is just the way they use to describe the arrangement. So no need to draw, no need to think of. Just know the word endless. Giant, sorry. Now, physical properties of metal. Primary school, you already learned malleable and ductile. You know these two words? Malleable means can bend. Ductile means can stretch. Both essentially say that they are soft. Pure science, please be copying. Both descriptors are just trying to tell us metal is soft. But then you'll be thinking, how come metals are soft? Are metals supposed to be soft? Look at this. This metal, is it meant to be soft? Obviously not. So how come I say metals are soft? Okay, pure metals are soft. Okay, just need to know that. Pure metals are soft. When I make it impure, it becomes hard. So now, what do you think is better? Is it a pure metal or impure metal? Impure. Anything that is hard is not pure metal. Pure metal must be soft. What is the reason of them being soft? Because they are all in regular size layers. Because each ion must be the same size now. They're all the same thing. They all lose electrons, so it doesn't affect the size. If you make a push, they can slide. So if the layers of atoms can slide past each other, then it's considered soft. Okay, I'm going to speed up now. High MPVP. Why? Because I need large amounts of energy. How come I bolded the word overcome? Because I'm pairing it with the word. Y'all can answer also. Overcome the strong electrostatic forces. you pair the word force with overcome. When do you use the word break? When you're breaking? Can check. You break can check. Look. What can you break? I told you the choice of word, if you mess it up, you literally get 0. What can you break? Or maybe, sorry, maybe it's not, is it not inside? Because you all don't need to learn. Sorry. Because you all don't need to learn the giant. Okay, pure science, you all must know. Whenever you break, you are breaking a bond. When you overcome, you're overcoming a force. So it's English. They just care about this. So since we are talking about electrostatic forces, then you must overcome. And of course, you say more. What is electrostatic forces between cation ions and CO? So it's just repeating that definition again. Now, this one you can participate. Are they an electrical conductor? They are. Why? Because they have, it's obvious, they have a lot of electrons that are mobile. Just now they kick out already, not attached to the atom, kick out already. So can conduct. Good conductor of heat, same reason. Because when you heat up the electrons can run around and pass the energy. So metals, you already know your frying pan. Those who take physics, you take physics. You know the frying pan is a good conductor of heat. Why? Because it's metal got electrons. Okay? So metals quite fast, nothing much, just like that. Now, this picture is only for pure because for combined, how come I don't give you this picture? Because you all don't need to know this. You all don't need to know this. That's why it's just ionic or simple covalent. So it's just one weak, one strong. You understand? So for your combined, you just need to know why it's weak. The only time you say the word weak, it goes with intermolecular forces. The only time for combined, the only time you all say strong, it goes with covalent forces are strong, but sorry, I should say 2 times. So internally, the covalent ones are strong. Ions are also strong. Ionic ones are also strong. Okay, but very seldom they will ask. Maybe they'll ask you. They ask you when you vaporize water, what are you breaking? What are you overcoming? What are you not breaking? You are not breaking the covalent because it's strong. So you're alright. Okay. So this diagram is more important for pure because there are many things to think about. This is a summary why we say electrostatic is strong. What's the meaning of electrostatic and who fall under electrostatic? For y'all know you all just need to know one type of electrostatic, that's ionic. Okay, and then this table, this chart is for y'all to also know electrostatic and covalent are all very strong. Strongest is covalent. It's very easy to confuse that you think covalent is the weakest. Even maybe last year you thought covalent. Many people thought covalent, but covalent is very strong. The only weak guy is BDW. Okay, so whenever you're a bit lost, come back to this chart to generally compare the strengths. Okay, we are done with these notes. There is a quiz. Everybody has a quiz. Y'all go to the quiz first. Next page. The quiz. Okay. Questions are different because okay, as I said, for combined, really no big deal. Combined, because you only got either or. If it's covalent, you know that it's the discrete simple molecules. They can just vaporize easily. If it's strong, it's ionic. Ionic or strong electrostatic. So your questions won't be so advanced. For pure, these questions are difficult, and I want you all to all look at the top. See, this is the note that you must memorize. You must memorize how to answer all this, how to explain and get full marks. I really even think last year I saw your papers, you're not good at explaining. You're not good at knowing exactly what to say, how much to say. So please, how do you answer open-ended question? For combined, you only need covalent ionic. For pure, you need covalent ionic or metallic. This just also write down. Covalent also got 2 types. You must be clear. It's either simple or giant. For combined, no need lah. Okay, for combined, your covalent only is simple. So you identify the bonding first. This guy, substance A, is a simple covalent molecule. Therefore, it can blah, 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 blah. Or we can say substance C is an ionic compound. Therefore, blah, blah, blah. So you must first tell them what is the bonding. Then you tell them what is the structure. For pure, as I said, molecular, you got simple, you got giant. Then ion, the description of their structure, just memorize is giant crystal lattice. The word giant means endless because you can have unlimited Na and Cl, NaCl, 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 all together 1 billion pieces, doesn't matter. So it's giant. Anything that have word giant means endless. So you can have giant crystal lattice for ions. You also can have giant metallic lattice. So more things to memorize for pure. Then because of the bonding and structure, please understand, you need to tell them the bonding. You need to tell them the structure. Then you can start to explain. So, for example, I answered. You can just listen to how I answer part C lah. C in the pure worksheet lah. So you have the different worksheet later. You do yourself. They ask you which substance in the combination of CO and Na. These questions are not easy, by the way. I can combine them anyway, and I want a substance that can conduct electricity in aqueous and molten. What is it hinting? I'm looking for which bonding. Which bonding do you see that this guy can conduct electricity when I make it aqueous or molten? Ionic. Everything was ionic. What do you think? It must be ionic. Then I look at the question, what ionic compound can I make up of CO and Na? I must have metal, no metal. So you can answer this also. I don't even know, is this in the question? It doesn't matter. Yeah, but you can answer. So out of CO and Na, how do I make up an ionic compound? Please, today pure science very quiet. Can you give me an answer? CO and Na, how do you make an ionic compound? It's not difficult. You just need to choose them. There's only one metal, nothing to choose.
Oxygen and sodium.
Yeah. Oxygen, sodium. So what is the compound? OA, ONA, like that. ONA. Is it?
I don't think so.
NaO. Now, is it?
NaO2, something like that.
I'm writing a few options. So I asked ONA, probably not ONA. So is it NaO2 or NaO? Somebody tell me yes, no, agree, disagree. This one is easier.
NaO2.
Oh yeah, just tell me say NaO2. You all also learned this already, you all can tell. Someone also said NaO2. Kelly, very good. Kelly saved the day. It's Na2O. Why are all of you wrong? Because you must crisscross Na plus and O2 minus. Whenever you're making ionic compound, you cannot just happily grab. Some people will just say NaO lah. Then, Xianghui, when you say NaO2 means you put an effort, you try to crisscross, but you crisscross wrongly. Do you see how you got it wrong? Because the two must go diagonal, you must trade. Right, so it's NaO2. So the answer is NaO2. Na2O lah. So this part, the first part I'll answer. But to finish, how do you explain? We use the guide again. So I have identified as Na2O. So I say sodium oxide is I follow here. Using this guide, what must I say? Sodium oxide has what bonding? Wait, ionic bonding. So you can say it's ionic, or you can combine point A and point B lah. You can say sodium oxide is ionic and its structure is a giant crystal lattice. Okay? And then use it to explain conductivity. So what do you say? Then you must read the notes. So you can copy. So after you set already, you must go back to your ionic notes and see. Then you must copy this. When in molten or aqueous state, ions, don't just say ions because we know this question. This question is talking about, you can say Na plus and O2 minus ion. You show off, you show off your knowledge. I mean, you copy word for word should be okay, but you want to show off. You say the sodium plus and O2 minus ions are not held in crystal lattice in liquid or when dissolved in water, therefore able to move freely to carry the electrical current. Every single word you copy down. Then you get the full marks for a question like this. Oh, sorry, it's far away. Yeah, you understand? So these kind of questions are hard to solve because you need to say all the correct words. Okay? Can I give you all the next 10 minutes to work on this? Okay? Y'all can discuss, y'all can ask me. Combine, y'all have a slightly different worksheet, so y'all can work together. In fact, y'all can discuss. In fact, y'all can go together. I mean, y'all can work individually first. If you're struggling, you can discuss. The three.
So, I don't really understand.
What do you not understand?
Like the metallic part, like the first part of the note.
Sorry, which part?
Like the first part of the metallic note.
First part of metallic. You're talking about how a metal is structured, is it?
Yeah, like what does it mean, like give up the valence electron?
Because the general idea for bonding, the general principle of bonding is we want to be stable. So lithium, for example, is unstable because of this guy. Right?
Yeah.
So imagine you have 1 million pieces of unhappy lithium atom. They gang up together. So they all will happily eject their last electron. And then this electron end up surrounding and wrapping them up and holding them as a piece of metal. While all of the lithium becomes stable. So it's like by all means, you just want to stabilize. If I can stabilize, I will stabilize. And when a bunch of metals come together, they can stabilize by each ejecting the unwanted electron and letting it wrap them up. That's just how they work naturally. Can?
Wait, so it's like all metal need to give up, like
all metal, because all metals got extra electron. You look at your periodic table, sodium got 1, magnesium got 2 extra electrons, aluminum got 3 extra electrons. They all want to kick it out.
okay.
So there are 2 ways, now you know there are 2 ways that metals can stabilize now. I can form a piece of metal by kicking out all my electrons and ganging out my friend. They also can do ionic bond. Right? Earlier we talked ionic bond. Ionic bond is just metal stabilizing, but at the same time he hang out with somebody else. Like see, sodium. This sodium can exist as a sodium metal if he can find enough sodium atoms come together, they all kick out this electron. But what if he happens to run into a chlorine? Then no need to do metallic bond. I can just give him. You see? So this is his own method to become stable. I can ionically become stable. Right? So this sodium can stabilize in a sodium chloride. It also can stabilize in a sodium metal. And
Wait, then when do you need to know like when to use metallic bond or like ionic?
no, you don't use that. The question will tell you, The question will tell you. So they will say a compound of sodium and chlorine. Then you describe. They ask you how would the melting point be for a compound that is made of sodium chloride. Then you must think, oh, sodium chloride is ionic. Then you answer accordingly. So they won't ask you to, they cannot ask you, will sodium form a sodium chloride or sodium? They cannot ask you because you don't know. It depends on how you found it, how it is presented to you. But you need to know that it's available. Sodium can stabilize in ionic compound or stabilize in a metallic structure. That's all you need to know. Then see the question. So we go back to the worksheet. Guys, next week we will continue this week. I don't think we can finish it today. But what's happening in this worksheet is, for the pure one, it's a bit harder. Let me just also open the combined one in case I need help. Okay, so for combined, you are doing carbon, oxygen, and chlorine. So, okay, let's look at A, 1A for pure. 2 substances that can conduct electricity in solid state. So it must be, what must you all be thinking? Or anybody has an idea already? What's the answer? That's for pure. You all can carry on. Pure students, you all know what's good or not? What are the 2 substances can only use CO and Na, so the choices are very limited. One of them is very obvious. Hey, all don't know.
C.
C, but in what form?
You mean
Diamond
A?
form? Huh?
What A?
What A?
What A?
Asking,
One
I
A.
know I'm asking 1A, but
Oh,
you cannot
okay.
just say C because C can be diamond.
In
Diamond
the
cannot. You must say the correct one.
other one, the graphite.
You're there already. Huh?
Graphite.
Yeah, so the answer is graphite. What else? So you must answer, you must explain graphite. You must leave some space to explain graphite. There's one more. Graphite is correct, but I said two substances. Quick. Hey, nobody knows. This is not difficult. Can it be ionic?
Yeah.
Ionic can conduct in solid state.
Oh,
Sorry, Clarice, say something.
wait, I thought they can't.
They can't, so it's wrong. So I'm asking, can it ionic? Answer is no. So it must be what? You use covalent already. You say ionic cannot, must be metallic. So it's sodium metal. That's it. Right? No need to bond with other things, bond with itself. So you have to explain why metals can conduct. Now B, tell me, this one easy. B very easy. Everybody should know.
Carbon.
Those just say, no, Xianghui, you keep saying
diamond.
people don't know what you're talking about.
Diamond.
It's a diamond. Okay, then explain why diamond is hard. This one I already said is NaO2. Who is gaseous? What two substances are gaseous in room temperature?
Water and H2O. Wait, no, water.
No water. No,
Hydrogen.
I'm only let you do CO and Na, so you cannot use water. No water, no H.
Oh, then oxygen.
And O2. One more. You're doing well. You got it already. You got the idea already. So you're thinking simple covalent, which is correct. Nobody knows now. We just need another simple covalent. Oh, Kelly said it. CO2, exactly. So these are the two. Then you explain. You explain using my notes. Okay. For combine, let me help you also. So combine, I'm opening my question on my screen. So you need carbon, oxygen, and chlorine. For A, what is the substance that can conduct in aqueous or molten?
Chlorine.
Hey, no leh, why? I made a mistake. I want to say sodium. Okay, can I, sorry. I mean, sorry, we still have time. I meant to say sodium. Can I change the word carbon to sodium? My bad.
Because we like supposed to spell out, or like we're supposed to just write O2.
Say what? Oh, when you say chemicals, you can write chemical formula. No need to spell. Yeah. Okay, sorry. For combined, sorry, I wasted your time. I wanted Na. Okay. So for A, actually, it's supposed to be ionic, so it's sodium chloride. Right. Then you explain. For B, two compounds that cannot conduct no matter what. That means cannot conduct must be covalent, because ionic sometimes can conduct. So what covalent compounds can you make? Can you make all of this? What compound? It's not easy, but y'all can. Just give me one also can. One compound is enough. It must be covalent. and it must be covalent means non-metal, so oxygen and chlorine. So how do you bond oxygen and chlorine? Ask yourself how many sticks, no? Oxygen needs 3 sticks, is it? Check. They don't know this thing. Memorize periodic table, man. Right. 2, then chlorine needs 1 stick. So what is the only logical way they bond? Cl2O. Right, yeah, so that's the compound that you haven't learned but you know is correct. Okay, the one is enough. C. 2 elements that are gaseous. So you want to be gaseous at room temperature. Of course, I haven't explained now, you must go and explain. Okay, for C, 2 elements that are gaseous. So elements that are gaseous. It's a trick question. O2 and Cl2. Yeah, then you explain accordingly. Okay.
CO2 is gaseous.
Yeah, it's gas. It's gaseous at room temperature because covalent compounds are very easy to vaporize. And all the explanation is in the notes now. Okay, so knowing the substance, you can go and slowly answer. The rest is just copy notes. Okay, we have 3 more minutes now. I will let you all carry on filling out the blanks, ask me any questions. Your homework is just the final 2 pages of all your notes. Okay. So next week I'll go through the answers. Sorry, you'll look at the screen for a while. Your homework will be all these sentences plus this page. This page, I got some sample answers. I'm not going to tell you much about it first. So go and try. You can kind of copy it. I mean the same stuff. O is atom and H is atom. Now you can fill in the blanks. Use a pencil. If anything wrong, we'll talk next week. Okay? Yeah. So for the rest of the time, 3 minutes left. Just do as much as you can, and I'll let you go on time. Use the toilet. Do we have any questions? Because I'm about to let you go. Zoom students, are you all just busy working? Any issues with the concepts you can ask now? Like just now, I think Clarice asked a good question about sodium, metals in general, how they bond. Anything else you'll find a bit weird or uncertain? Feels like a no. Okay, the homework is, as I said, this page and try to fill in the blanks. Next week we'll finish this up. There are hints. You can look. And then this one mainly I give you the answer already. For question 2 and 3 are a bit advanced. It's the same question for pure and combined. So question 2 and 3, you can Google, you can ask your friend. But it's quite interesting to think about all this, okay? That's it. We are done. AMAT student, take a 30-second break. Send me your homework. I have search homework. I haven't received anything. Camp students can go. AMAT students, if you couldn't do or I'll never do, it's okay. We're not gonna score you. Okay, thank you. Bye bye. Go. 1 minute break. 1 minute. Go. Thank you.